Hello. In this exercise, we're going to solve a problem that requires evaluation of properties, evaluation of an extended system state. The system state is covered in chapters 0 and 1 of this textbook. And we are going to use the simplest model known as the SL model, which handles properties of solids and liquids, and different models are covered in chapter 3 of the textbook. So let's begin with the problem statement. So here we have a block of copper, an iron projectile, not a copper, iron projectile. At state 1 information is supplied here, and state 2 informations are supplied there. And we are asked to find the change in the stored energy of the system and how much of that contribution is because of change in velocity, change in height, etc. So I have already logged in to test, and I'll launch a test calc by clicking here. And since we are going to evaluate state properties of system state, so we click here, and finally click on the SL model to launch the test calc. You can see several tabs. Hands-on example, this particular video is going to be right here. That's what I'm recording right now. Then you can go to the discussion tab. If you see a problem or something, you can post a question here. And we're going to use the HTML5 version of test calcs. These are compatible with any browser, even iPads. So as you can see, it looks a little bit complicated, but once you understand how it works, you will see all test steps behave very similarly. First, you will see what we are seeing here is the state panel, and then there's a graphics panel, and there's an I/O panel, and clicking on the question mark brings up the help panel. Over there, you can show or hide generally what each panel what is capable of doing. And you can always go back and forth among different tabs. Suppose you're seeing a video here, you can come back and solve a problem there. So let's begin with the problem at hand. Instead of explaining everything here, as we solve the problem, you will see that how intuitive it is to use this test calc. First off, at the bottom you will see a help panel. So as the pointer goes over any variable, as you can see, the meaning of each variable is shown. Now this is a state panel. State means a collection of properties. And as you can see, there are properties that are kind of color coded. There are some blue colors, these are called thermodynamic properties that describes the equilibrium, etc., etc. So to solve the problem, let's select the material first, which is iron in this case. And if you just click a calculate without doing anything, you will notice that some of the properties, the red properties, are calculated. These are the material properties. As soon as you know the material, you know these values. It doesn't depend on the particular equilibrium the system is in. Okay, what other properties are given here? The temperature is given. I can click anywhere to trigger the temperature, which is 30 degrees Celsius. Now, notice that if you now click on, say, you want to put in what is internal energy, the test calc will not allow you to. The test calc will not allow you to enter this value. If you click here, a message comes that the property U is a dependent property, so it prevents you from making a mistake. But you could enter pressure, for instance, which is not known in this problem right now. Anyway, so with the temperature, if you calculate, see some of the properties are calculated, which are dependent solely on temperature. The mass is supplied. We can enter the mass to be 50 kg and click the calculate button or the enter key in your keyboard, and some more properties such as volume is calculated. If we knew the pressure, in this problem it is not given, but suppose the iron block is sitting in atmospheric air, which is a pressure of 100 kPa. Notice that now more variables will be calculated. It's taking a little time because the server is having some issue right now. Okay, so as you can see, more and more properties are being calculated as we enter more properties. Finally, phi and psi, these variables are called exergy. They depend, what phi basically means is how much of the energy of the system can be extracted for useful purpose. This concept is an advanced concept covered in chapter 6, but just to, if you know what exergy is, at least you can play with it. So to calculate the exergy, you've got to define what is known as the dead state of the system, which is, suppose the atmosphere is 100 kPa and 25 degrees Celsius. So you put in the atmospheric pressure and temperature and calculate the dead state. Now if you come back to state 1, you will find the phi and psi are calculated. These are stored and flow exergy respectively. Anyway, I'm getting ahead of this problem. In this particular problem, pressure is not known, so let's make that unknown. And if we now calculate, you'll notice that without the pressure, phi and psi is not calculated, and some of the variables are unknown. So now let's go to state 2. I can just click this button or select it from there. Notice that once a state is calculated, it is shown with a calculation sign in front. Now state 2 is not known. And what is given in state 2 is that the temperature is 300 degrees Celsius and the velocity is 50 meter per second and the height is 50 meter per second. The elevation of the system, 50 meter. And of course the mass of the block is not changing. So we'll enter an equation, m2 equals m1, and this is a very good practice always. Now if we do a calculate, all the properties that can be calculated are found, and notice the stored energy is E, which is calculated here. So the question is to find delta E, the change in stored energy. So if you go to the graphics panel, you will notice that the calculated states are shown here. And in the I/O panel, a lot of things can be done here. So to solve this particular problem, we want to find what is change in energy. So I'm writing an equation, delta capital E, suppose we declare that as a variable, equals what? M1, of course M1 and M2 are equal, so I can just write M1 star E2 minus E1. I can put a semicolon and I click the enter button and it calculates exactly how much is the 6162 is my delta E. So I may write it down 6162 in the PowerPoint that we are doing. So delta E is 6162. Okay, going back to the problem. Oh, unfortunately the PowerPoint writing doesn't work. So let's remember that 6162 is our delta E. Next question is, what is the contribution of kinetic energy? In other words, we see that the temperature has changed, velocity has changed, height has changed. So just get rid of the velocity change. Suppose we set velocity to be 0. That means there is no velocity change in this problem anymore. I recalculate. Now look, if I go to the I/O panel, that particular equation that you wrote down, you can reuse it. All we have to do is to calculate, and a new value for delta E is found, 6099. So like that, you can communicate between the I/O panel and the state panel. And that's a very powerful tool. You can write an equation here or a variable here. Suppose you could write here, for instance, we can write P equals 100. And as soon as it is read, P equals 100, we can go there. If I want, I can say P2 equals P and do a calculate. As you put the variable pointer over the variable at the top, at the top panel, you'll see the value show up. Can we see P2 equals P equals 100? That's what is shown in the top panel. So you will find many other features that we brought out gradually as we solve more and more problem. Again, to use this tool, you don't have to know everything right now. All you have to understand is that a state is kind of an encapsulation of properties of equilibrium. So if you know a few of the properties, everything else can be calculated. As a system goes from one state to another, a lot of interesting things would happen. And that's what thermodynamics is all about. So let me stop here until we meet again in another solved problem.